Good day, everyone. So today we're going to talk about nonparametric statistics. Now, this topic was feathered into a lot of the chapters. However, we're going to just sort of split it out and make it its own little topic. Actually, it's a fairly large topic. It's just that we just want to introduce it here. So all the previous inferential techniques either required that the population distribution or distributions were normal, or that the CLT applied. These techniques are called parametric statistics, so all the inferential stats that we ran so far were parametric. In other words, we verified, sometimes assumed, that the data come from a pre-described model, such as the normal model. So in other words, remember for like the t-test we said, well, either x has to be normal or n has to be greater than or equal to 30 for the central limit there imply, right? So in other words, we verified that the data come from a pre-described model that are determined by a small number of parameters, such as regression. Okay, so with regression, you had a population line, right? You had a population regression line. Within that population regression line, you had a population slope and the population y-intercept. Well, what happens if these models don't apply, meaning the assumptions were violated, or if you will, the conditions were violated? Or we simply want to test something other than what was tested prior. For example, instead of testing the population mean, maybe we want to test the population median instead. So in other words, when do we use non-parametric statistics? When the conditions/assumptions were violated, or we want to test something other than what was tested in the parametric test. All right. So these techniques do not require population distributions to be normal. Okay, so we don't need the populations to be normal, all right, or based on any other distribution, and that the structure of the model is fixed, such as with regression. Non-parametric statistics can actually have parameters, but the number and the nature of the parameters are very flexible, okay, and not fixed in advance. So it just depends on the situation that you have, and you say, oh, okay, we can use this probability distribution to figure out the p-value, but the original data doesn't have to be originally normal or anything like that, all right? So non-parametric techniques are very robust, and what do I mean by robust? What I mean by that is that they work in most situations. They have little to no conditions/assumptions. So you might be asking yourself, well, why don't we just use these techniques instead of the parametric ones? And there's a very sound reason why. The reason why is that the power for these techniques are going to be lower than their corresponding parametric techniques. Remember, we talked about power. Power is the probability of rejecting the null when we should have, or if you will, accepting the alternative when we should have. So the power will always be higher with the parametric techniques than their corresponding non-parametric techniques. And remember, we want power to be high, especially when if we're a researcher, we want the power to be high when we go ahead and run our test. And so, if we can run the parametric techniques, we should. All right. So on the left-hand side, you have the parametric techniques. So you have the t-test, the two-sample t-test, the paired, okay, so on and so forth. Well, over on the right-hand side, those are the most popular non-parametric techniques corresponding to the ones on the left. All right. There's actually more parametric techniques. So for example, you might have 3 or 4 non-parametric techniques for every parametric technique, because it just depends on the situation that you got, and you're kind of flexible about how to do things. All right. So an example is the sign test. The sign test is where we will test the population median and not the population mean. Here we will not assume anything about the population, such as that it has to be normal, okay? So the original data doesn't have to be normal, okay? The only conditions necessary is to have continuous data and a random sample. That's it, okay? So let's go through the logic of the test before we actually perform it. So here's the logic. We randomly sample students that just graduated with a bachelor's degree from college. We ask them to calculate the out-of-pocket expenses, so they have their outstanding loans and money already paid to get that degree. We test whether the median is 60,000 60K or not. So let's say that we randomly select 100 students. Now, probably this isn't too realistic because the CLT would probably apply in this situation, but I need to use a larger sample size here to kind of prove my point, okay? So just kind of bear with me that we're going to use a larger sample size than normally what you see with nonparametric statistics. And again, it's just to prove a point. So let's say that with our 100 students, we find 25 that are below 60K, and we have 75 above 60,000. So what do you think about that? You got to so you got to keep this in mind, is that if the population median is 60,000, we should have then 50% of the observations above and 50% of the observations below 60,000. So if truly the population median is 60,000, we should have 50 above, 50 below as far as the number of observations. But we had this 25-75 split, all right? So with this kind of split, do you really think that the population median is equal to 60,000, or is it something else? And hopefully you say, it's probably what? It's probably not 60,000, but it's probably greater than 60,000 because we had so many more. We had a 75-25 split, 75 above 60,000, all right? So hopefully you say that the median is probably not 60,000, but higher because it's unlikely that we took a random sample and by chance we would produce that many students above 60,000. And if you kind of thought that through, you're thinking in terms of statistics. Why? Because that's the p-value, all right? So let's say that we got the following instead. And so instead of that 75-25 split, maybe we got a 48-52 split. Now does that tell you something else? Well, what do you think now? Is this enough evidence for you to say for certain that the population median is greater than 60,000? Well, I wouldn't be too confident with that. All right. Why? Because if you think about it, if the null had the population median at 60,000, and if we took a random sample, don't you think a random sample could have been produced, could have produced this, meaning a 48-52 split? Okay, so that's not very well, that's not overwhelming evidence here. Okay, and certainly a random sample could have produced this if the population median was truly equal to 60,000. So we probably, in that case, wouldn't have, we would have said do not reject the null hypothesis in that situation. So that's how the 20,000 foot view of this test is run, okay, and its logic. So here are the steps for the sign test. First of all, the null hypothesis will be the population median will be equal to some value, whereas the alternative, the population median is greater than, less than, or not equal to that same value. So no different than from before. Now here, pay close attention to this. The value of the test statistic is always, always, always what we call S plus. No matter if H sub A is less than, greater than, or not equal to, you do not change the value of the test stat. It's always S plus. And what is S plus? It's real simple. S plus is equal to the number of observations greater than the value of the null. That's it. All we do is count the number of observations above the value of the null and below. And that's it. All right. And that's what happens a lot with these nonparametric techniques. It's very simple in working with the data. Okay. Or you might have to rank the data and then figure things out. Okay. So the working with the data is actually fairly simple. S minus. Now there is an S minus. What is S minus? It's the number of observations less than the value of the null. Now you do have to be careful. You do have to be careful about the next thing here. N then is equal to S plus S minus. It is equal to then the number of observations not equal to the value of the null hypothesis. So if you have observations that are exactly equal to the null, basically they get thrown out because it doesn't give us any evidence, okay, that the median would be greater than or less than that value in the null. All right, so you throw them out. So n is the number of observations not equal to the value in the null. All right, so if h sub a has a less than sign, the p-value is equal to the probability that x, okay, I'll get to x here in a second, is less than or equal to, and that's not a mistake, less than or equal to s plus. If HA has a greater than sign, the p-value will be equal to the probability that x is greater than or equal to s plus. So notice s plus is the value of the statistic no matter what, okay? And we do have to include the equal to sign there. And then if HA has a not equal to sign, it's a little bit trickier, but not that tricky. The p-value is equal to 2 times the smaller of either one of these. And so whichever one is the smaller one, you multiply it by 2, and that's your p-value for a two-tailed test. All right. What is x? X is binomial if you think about it then. X is binomial. All right. So so the original data didn't have to be any type of probability distribution like being normal or whatever. Okay. But since you decided just to simply count the number above or below, sounds binomial to me, right? Two possibilities. Okay. And so you would have a binomial here where n is equal to s plus plus s minus, and p is just simply equal to 0.5. Now you're saying, hold on, well, why are we setting p equal to 0.5? Well, the reason why is because we assume the null is temporarily correct, okay? And what's in the null? The population median is equal to, I said mean, the population median is equal to some value, and you either have, and that means you got 50% above, 50% below, okay? And so that's how we're going to figure out the p-values, just using the binomial. So here's an example. We randomly asked 16 UA students how much they spend on textbooks this semester. Test if the population median is less than $500. So here's the data, all right? I want you to notice something here. There is one observation that is exactly 500, all right? So we have to calculate S plus, S minus, and N. S plus would be 3. We had 3 observations here. We had 1, 2, 3 that were greater than 500. And what about S minus? All the other stuff, okay, other than that 500. So we have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we had 12. And that means N is equal to 15. N is equal to 15, okay? So if we started off with 16, one was exactly at 500, we throw that one out, and we're left with an N of 15. Population mean is equal to 500. For the null, the alternative, population median is less than 500, because that's what we were testing. Verify the conditions. The data is continuous, okay? It's money that's continuous, and we took a random sample, all right? And so we have our conditions. We continue. So what would be the p-value? The p-value would be the probability that x is less than or equal to s plus, which is 3, where n is equal to 15 and p is equal to 2.5. All right. So you would just go to the binomial table. You could go to the binomial table, or you could use StatCrunch. Either one, right? So let's say that we go over to StatCrunch. So we got here, so let's get out of this. And we'll go into StatCrunch. There's StatCrunch. So we go to calculators, stat calculators, and binomial. And here we're going to put an, we don't want an N of 1,000. We want an N of 15. We want a P of 0.5. And we're trying to figure out the probability that X is less than or equal to, I think it was 3. What do we get for a p-value? I got here 0.0176, 0.0176. So notice I have the p-value right there. So I'll go back into the slideshow here. I just got to let my computer catch up. There we go. All right. And since the p-value is less than alpha, we're going to go ahead and reject the null. And we have strong statistically significant evidence at the 5% significance level that the median dollars spent on textbooks this semester is less than $500 for what? All the students. For all the students. Okay? So, just a quick little introduction to nonparametrics and our sign test. Okay? Maybe I'll ask you a couple of questions on the sign test and maybe some logic behind um, you know, just some thoughts with regards to nonparametrics on the final. Okay, that's it. That's the end of all the lectures. Thank you for your time this semester.